Georg Simon Ohm was a German physicist born in Erlangen, Bavaria on March 16, 1787. As a high school teacher, Ohm started his research with the recently invented electrochemical cell, invented by Italian Count Alessandro Volta. Using equipment of his own creation, Ohm determined that the current that flows through a wire is proportional to its cross-sectional area and inversely proportional to its length. This is otherwise known as Ohm's law. Using the results of his experiments, Georg Simon Ohm was able to define the fundamental relationship between voltage, current, and resistance. These fundamental relationships are of such great importance that they represent the true beginning of electrical circuit analysis.
Hi, I'm Blake.
And I'm Chelsea.
And we're going to do an experiment to demonstrate Ohm's law.
What is Ohm's law, Blake?
Well, Ohm's law says that the electrical current flowing through a circuit is equal to the voltage divided by the resistance.
How are we going to test it?
I'll show you. Go.
In this lab, we're going to demonstrate that when voltage increases and the resistance is constant, then the current through the circuit increases. These are our supplies to do the lab experiment. This is our multimeter that we connect to the resistor. These are 10 Duracell 1.5 volt batteries. These are the 10 containers that we use to put the batteries in, and they connect like so. These are 2 alligator clips that we use to connect the blue things. And this is the resistor. It's really small.
So we take the red wire and put it into the red outlet when we're testing the resistance of the ohmic resistor. And we plug it into the white outlet when we're testing the current that's going through the circuit. Okay, so we're going to complete the circuit on the multimeter with this ohmic resistor. Okay, the resistance of this ohmic resistor is 560 ohms.
Okay, so this is our first battery, and we have the red wire running through to the red alligator clip, connected to the battery, and the battery connected to a green alligator clip, which is connected to the resistor, which I will take the black cord and put it against to measure the resistance. And then on the multimeter, we'll see what it reads. The current through the circuit for the first battery is 13.4 times 10 to the negative 6 amps. For 2 batteries, the current through the circuit is 12.5 times 10 to the negative 6 amps. With 3 batteries, 1, 2, 3, the current through the circuit is 11.5 times 10 to the negative 6 amps. For 4 batteries, the current through the circuit is 10.3 times 10 to the negative 6 amps. 1, 2, 3, 4. The current through the circuit of 5 batteries is 9.2 times 10 to the negative 6 amps. Okay.
The electrical current through a pumpkin is about 12 times 10 to the negative 6 amps. The current through the circuit when there's 6 batteries connected is 8.6 times 10 to the negative 6 amps. The current through the circuit when there's 7 batteries attached is 7.3 times 10 to the negative 6 amps. Now we have 8 batteries attached to the circuit, and the current flowing through it is 6.6 times 10 to the negative 6 amps. With 9 batteries attached to our circuit, the current flowing through is 5.2 times 10 to the negative 6 amps. Finally, with 10 batteries connected to our circuit,
Woohoo!
the current flowing through is 4.5 times 10 to the negative 6 amps.
After
after we compiled all of our data, we made this graph. But before that, we have our variables. Our independent variable is volts, and our dependent variable is the current through the circuit.
In our table, we have the trials, the resistance, the volts, and the currents measured in amps. And the resistance is measured in ohms, and that's the symbol for it. In the first trial, the resistance was 560 ohms, the volts were 1.5, and the current was 13.4 times 10 to the negative 6 amps. In trial 2, the resistance was again 560, there were 3 volts, and the current was 12.5 times 10 to the negative 6 amps. For trial 3, the resistance was 560 ohms, it was 4.5 volts, and the current was 11.5 times 10 to the negative 6 amps. For trial 4, it was 560 ohms, 6 volts, and 10.3 times 10 to the negative 6. For trial 5, it was 560 ohms, 7.5 volts, and 9.2 times 10 to the negative 6 amps. For trial 6, it was 560 ohms, 9 volts, and 8.6 times 10 to the negative 6 amps. For trial 7, it was again 560 ohms, 10.5 volts, and 7.3 times 10 to the negative 6 amps. For trial 8, it was 560 ohms, 12 volts, and 6.6 times 10 to the negative 6 amps. For trial 9, it was 560 ohms again, 13.5 volts, and 5.2 times 10 to the negative 6. And finally, for trial 10, 560 ohms, 15 volts, and 4.5 times 10 to the negative 6 amps. We have now put our information into a graph. On the x-axis, we have volts, which goes every 1.5. And then we have current on the y-axis, which is measured in 10 to the negative 6 amps. So we put each of our points corresponding with the x and y axis and connected them for the line of best fit.
For our mathematical model, we have y equals negative 0.668 volts plus 14.42 amps. And we got that by taking the line of best fit from our data and then finding the slope and y-intercept of that data. In conclusion, we learned that the current flowing through a circuit is equal to the voltage divided by the resistance.
We also learned that the current is directly proportional to the voltage because there is a line on the graph. Thanks, Mr. Ohm.